In this lesson, we are going to introduce the 4 types of solids and look at the properties that we will focus on in this module. So the first of the 4 types of solids is ionic solids. And ionic solids are made up of positive and negative ions. The positive ions are called cations and the negative ions are called anions. When we look at the structure of an ionic solid, we see that each positive ion is surrounded by negative ions, and each negative ion is surrounded by positive ions. And this extends in 3 directions. So it's extending this way, along the side, backwards, and also up and down. We call this regular arrangement of positive ion, negative ion, positive ion, negative ion that extends in 3 directions a 3D lattice. So lattice just means a regular arrangement, and it's 3D because it's extending sideways, backwards, and up and down. In an ionic solid, the ions are held together by strong electrostatic attractions called the ionic bond. So if we look here, we've got a chlorine ion and a sodium ion. So the sodium has given its electron to the chlorine. So sodium's positive, chlorine or chloride, in this case because it's an ion, is negative. And then they are held together because the negative anion or the negative ion is attracted to the cation, the positive ion. And the attraction there for each positive ion for all of the negative ions around it, and each negative ion for all of the positive ions around it is called the ionic bond. So the second solid we look at are metallic solids, and these are made up of metal atoms of only one type. So in this case here, we've got all silver metal atoms. What is unique about the metallic solid is that the valence electrons of the atoms are delocalized. So what that means is for each silver, it has lost its valence electrons. They are no longer held tightly by the nucleus. And these valence electrons are free to move throughout the solid. And so we call that delocalized. So no longer attached and free to move where they want around the solid. So in a metallic solid, the nuclei, or the protons in the nucleus of each atom, is attracted to the delocalized electrons around it. And each delocalized electron is attracted to the nucleus, the protons of the atoms around it. So the atom has lost its valence electrons, so it can be thought of as a cation or as a positive ion. But because when we look at the entire solid, the number of protons and the number of electrons is the same, because those delocalized electrons are still moving around that metallic solid. They haven't gone and joined another atom somewhere else or another solid somewhere else. So we say that metallic solids are made up of atoms, because even though each atom has lost its valence electrons, so it's positive, the number of protons to electrons in the solid is the same. And so overall, that metallic solid is neutral. So we say metallic solids are made up of atoms, and they're held together by the electrostatic attraction between the nucleus of each atom to the delocalized electrons around it. And that attraction we call the metallic bond. So the next type of solid that we look at is the molecular solid. And this is made up of molecules, just like we've been looking at in Module 1. The atoms within each molecule are held together by these strong covalent bonds. And so these are really hard to break. But the molecules themselves are attracted to each other by very, very weak forces. And these are called intermolecular forces. Inter means between 2 different things. So if you think of something like cross-country, inter-school cross-country means you're competing with people from other schools. It's between lots of different schools. Whereas we call the bonds within one atom intramolecular. So sometimes you'll just see intramolecular and intermolecular used. Intra means within one school, so it'd be like you doing cross-country with everyone from your school. Intermolecular means between two different things. So you now going to inter-schools and competing with people from other schools. So when we look at molecular solids, we are focusing on these intermolecular forces, these forces holding the different molecules together. These forces are due to the attraction of the electrons in one molecule to the protons in a second molecule. These weak intermolecular forces are often called van der Waals forces. So in some of your textbooks, you might be reading about van der Waals forces, and it's just another name for the weak intermolecular forces holding the molecules together. So molecular solids can be made up of non-polar molecules or polar molecules. And we looked at what makes a molecule polar or non-polar in the last module. So with polar molecules, those weak intermolecular forces between the molecules are called dipole-dipole forces. And that's because with a polar molecule, it has a dipole. It has a negative end and it has a positive end. And the negative end of one molecule will be attracted to the positive end of a molecule next to it. And the positive end of the molecule will be attracted to the negative end of another molecule. And this just extends throughout the molecule. So these dipole-dipole forces, or the intermolecular forces between polar molecules, are slightly stronger than the intermolecular forces between non-polar molecules of the same size. So non-polar molecules, we say, have London dispersion forces. And you don't need to remember this keyword, but sometimes as you're reading it, you'll see that's what it's called, especially if you try to Google it. If you Google London dispersion forces, you'll get a lot more accurate information. And briefly, what that means is that when the electrons are moving around the molecule, just by chance, sometimes they all end up at one end of the molecule. And what that does is it repels all the electrons in the molecule next to it, because there's now this big clump of negative charges leaving this end of the molecule negative. And so when it repels the electrons in the molecule next to it, it leaves this end positive. And so now there's an attraction between the negative electrons in this molecule and the positive electrons in this molecule. And we say these are temporary dipoles because they don't last long. The electrons don't stay stuck there. A split second later, they keep moving, and now they're no longer all clustered over here, and that temporary dipole is broken, but it will form just by chance somewhere else in the molecule between another set of molecules. And it's this very weak attraction that holds molecular solids together. Our final solid that we look at is the covalent network solid. And just like molecular solids, these are made up of non-metal atoms. But the difference is that these non-metal atoms are all covalently bonded to each other, creating a long network that can extend in one direction, so backwards and forwards, two directions, backwards and forwards this way, and extending backwards this way, or three directions, so up and down, backwards and forwards, and in this way. At level 2, we just focus on the 2D covalent networks and the 3D covalent networks. In the 2D covalent network we look at is graphite, and the 3D covalent networks we look at are diamond and silicon dioxide, which is also called silica or quartz. The 1D covalent networks are made up of organic molecules, so long chains of carbons all bonded to each other, and each carbon usually bonded to hydrogen. So the covalent network solids are held together by really strong covalent bonds. So now we will look at the properties that we will focus on throughout this module, and I'll explain what these properties mean. So the first one that we look at is melting point and boiling point. So when something melts, it turns from a solid to a liquid. And for this to happen, some of those forces holding the particles together must be broken. So in an ionic solid, some of those ionic bonds have to break. And in a molecular solid, some of those intermolecular forces have to break, those van der Waals forces. And so when it melts, not all of the attractive forces break, only some of them do. But it's enough to allow some of the particles in the solid to move around a little bit more and start sliding over each other. So they're no longer held in a fixed position. The boiling point is when something goes from a liquid to a gas. And at that point, the majority, if not all of the attractive forces between the particles are broken. So this leaves each particle within the solid completely free of the other particles and able to move independently. So melting point and boiling point are based on how strong those attractive forces are between the particles in each solid. So the stronger the attractive forces, the harder they are to break. And so therefore it's going to take more energy to break those attractive forces, and the melting point and boiling point will have to increase. The boiling point will always be higher than the melting point. And that's because if you're melting something, you're only breaking some of those attractive forces. Whereas if you're boiling something, you're breaking all of the attractive forces. It's going to take more heat energy to break all of the forces than it will to break some. So you always have a boiling point that is a higher temperature than the melting point. So the next one that we look at level 2 is solubility. And solubility is whether or not something will dissolve in something else. So there are two key terms that we look at or that we talk about with solubility, and that's solute and solvent. So the solute is the substance that is dissolved, and the solvent is the substance that something is dissolving in. So if we think about making a cup of raro, you take a spoonful of solid raro and you put it into a cup of water and you stir it to dissolve that raro. The raro is the solute. That is the thing that's being dissolved. The solvent is your cup of water. That's what the raro is dissolving in. If something is soluble, then once it's been dissolved, you can no longer see it. It's mixed completely throughout the solvent. Whereas if the solute is insoluble, two things might happen. If you do something like add oil to water, oil is insoluble in water, it won't dissolve, and it creates these two different layers. So both are liquids, they're insoluble, and they create two different layers. Whereas if you're adding a solid that is insoluble, what happens is that it will usually just end up sitting at the bottom of your cup. And so you'll just see a solid at the bottom of the solvent. So quite often the solvent is water. And when something dissolves in a solvent, in this case water, what happens is that water molecules are completely surrounding each particle. And that's what dissolved means. It means that the particles in the solid or the liquid have been separated and they are completely surrounded by the solvent, by solvent particles. So in this picture, we have an ionic solid, so sodium chloride, made up of positive and negative ions, and we have our water molecules here. And water is polar, which means that the end with the oxygen is negative, slightly negative, and the ends with the hydrogens are slightly positive. And so if something dissolves in water, what has to happen first is that the attractive forces, the weak intermolecular forces between the waters, the solvent, have to break. And the attractive forces between the solute, between the ions in sodium chloride, have to break. And then new attractive forces have to form between the particles of the solute and the particles of the solvent. So for this to happen, first of all, the water molecules must surround the negative ions in the solute. And so we've got a negative ion here, so the hydrogen will come along and surround the negative ions. The attractive forces between the sodium and the chloride ions break, and new attractive forces form between the slightly positive end of water and the negative ion. And that's enough to pull this ion out of its structure, out of its 3D lattice. At the same time, the slightly negative end of water with the oxygen is coming along and it's surrounding each positive ion, each sodium ion, causing the attractive forces between the sodium and the chloride ions to break, the attractive forces between the water to break, and new attractive forces to form between the positive sodium ion and the slightly negative end of water. And so the water completely surrounds the positive ion and it pulls it out of its 3D lattice. So all of the exposed particles, first of all, are dissolved, and that then exposes new particles in the next layer of the solid. And then those are surrounded by water and those are dissolved. This will keep happening until either all of the solute is dissolved or we've run out of solvent particles. That's why if you keep adding RaRo to water, at some point the RaRo will stop dissolving and it will just start to sink to the bottom and you'll see solid sitting on the bottom of your cup. And that's because you've run out of water. All of the water molecules have been used up, dissolving, surrounding the RaRo particles. And so if you add more RaRo particles, there's no more water left to surround them, so they can't dissolve and they sink to the bottom. For something to dissolve, the solvent, in this case the water, has to be equally or more attracted to the solute than they are to themselves. And likewise, the solute particles have to be equally attracted or more attracted to the solvent than they are to each other. If they are more attracted to themselves, then the attractive forces between the particles can't be broken. So new attractive forces can't form between the solvent particles and the solute particles. And so that's what we see here. In this case, the particles within the oil are more attracted to themselves than they are to water, and the particles within the water are more attracted to themselves than they are to the oil. So the water does not surround the oil particles. So the attractive forces within the water particles and the attractive forces within the oil particles aren't broken. We call this like dissolves like. And quite often I think the easiest way to think about this is to think about two people in a relationship. So if they're happy together, they're not going to break up. That attraction between them isn't going to break. Someone has to come along that one of those two people in that relationship is more attracted to. And if they're equally or more attracted to that new person that's come along, then they'll break up with their current partner and they'll form a new bond, a new relationship with this new person that's come along. And so it's exactly the same with particles. If the particles within the solute or the solvent are more attracted to each other than they are to this new particle, this new person that's come along, then they will stay together. And so if they're happy together, they're staying together, they're more attracted to each other, they're not going to split or they're not going to break that attraction, that bond, to form a new relationship or a new bond with someone else. And so that's what like dissolves like means. A solute will dissolve in a solvent that is similar to it. It has similar bonds because the attractive forces within those bonds are similar. So they're a similar strength. If those attractive forces between the solute and the solvent particles are completely different, then they're not going to form new attractive forces between each other. All right, so the next one that we look at is hardness. And that's exactly as it sounds. It means if you were to touch the solid, would it be soft? Could you squish it, or would it be hard and really impossible to break? And hardness is also based on the strength of the attractive forces between particles. So the stronger the attractive forces, the harder something is. Malleable means, can you bend something or shape it without it breaking? You can take a piece of metal and you can bang it with a hammer and you can bend it, you can shape it without that piece of metal breaking. So that is what malleable means, is can we bend it, can we shape it without breaking the solid? Ductile is a similar type of property, but rather than bending something, it means can we draw it out into a wire? So can we shape it and turn it into a wire? The next property still related to hardness is whether or not the solid is brittle. So a brittle solid will shatter, it will break. So if you think of glass, that's brittle. It takes a fair amount of force to break the glass. You know, if you knock on the glass, it's not going to break. But if you take a hammer at it and you really, put all your force into breaking that window, it will break and it will shatter. So all of the attractive forces around where you hit are broken and the solid shatters. And so that's what brittle means. And our final one is conductivity. And this is whether or not a substance will conduct electricity when it is placed in an electric field. So in a solid, electrons or ions will move backwards and forwards. But when they are exposed to an electric field, the electrons will move in the same direction. So they're no longer just moving backwards and forwards. So here, when we expose something to an electric field, to a directional charge, now the electrons are going to start to move away from the negative end, and they're going to start to flow towards the positive end. They're going to be attracted to the positive end and move away. They're repelled by the negative end. So in this case, electrons or the anions, negative ions, will move in this direction, and they're all moving in the same direction. If those electrons or ions are free to move throughout the solid, then they will be able to carry that negative charge towards the positive end. So we say that they can carry a charge. So something that carries an electrical charge from one place to another, conduct, because it is carrying a current, and therefore it's conducting electricity. So those are the 4 solids that we look at in this module, and the properties that we focus on and what those properties mean. And so in the next 4 lessons, we are going to focus on each of the solids and explain their properties in more detail.